break actually had a good question. So I'm going to actually present it as an example. So when I mentioned that, you can have an independent circuit and that would do nothing and not affect the general transfer function. So this is a good example. I mean, you thought about an example with one of you guys, which was, so let's say this is your system. V in, some R, called R1, C1, V out. And let's say on the side, I say, for some reason, I decide that I have this thing on the side, and that's part of my circuit. So this is my whole circuit. I define such a whole circuit. It should still work, right? But let's see how it happens. So let's apply the method. What are the zero value time constants? Tau 1, 0 is simply R1, C1, and tau 2, 0 is R2, C2. And I have two independent energy storage elements. So basically I have two poles. That's what it tells me, right? This transfer function from this equal to the out. So it says tau 2, 1 is basically what? Tau 2, 1 is the resistance seen by this guy when that guy is shorted, which is the same as before, which is equal to tau 2, 0. So this is an uncoupled or decoupled pole, which basically is still R2, C2. Since they are uncoupled, I can refer to these as tau 1 and tau 2. I don't need the superscripts. Whenever everything is uncoupled, I can write it that way. So it doesn't matter. I can write it this way or that way. So let's calculate B1 and B2. B1 is the sum of these two. So it's basically R1, C1 plus R2, C2, which I could write as tau 1 plus tau 2. So the transfer function looks as tau 1 plus tau 2 S plus tau 1, 0 times tau 2, 1, which is these two, which is again, since this being tau, this is simply just tau 2, becomes tau 1 tau 2 S squared. So you say, wait a second. This is a first order system. And it doesn't have anything to do with this guy sitting next to it. How come you got a second order system? Well, we are not done yet. You have to look at the numerator, see what it does. So what is the numerator? So let's calculate, what is H naught? The first time, the transfer constant. Well, what is H naught? What? When? And what is H1? When C1 is shorted, is 0. What is H2? When C2 is shorted. The transfer function from here to there, and C2 is shorted. Is H1, or 1. And what is H12? When both of them are shorted, it's 0. So what do I have? I have H0, which is 1, plus H2 times tau 2, 0, right? Times S, which is 1 times tau 2 S. That's my transfer function, right? So this is the transfer function. So wait a second. This should have one pole and no zeros. You got 1, 0, and 2 poles. What's going on? Well, look at it carefully. The denominator can be factored. That's another way of saying that these are uncoupled. 1 plus tau 2s, but this is the same as that. So I got a pole and a 0 right on top of each other. As I should have. Which cancel each other. So I get 1 over 1 plus tau 1s, which is the transfer function of the system. So the method is consistent. Now, you also asked another question earlier about whether or not zeros are decoupled in general. Let me give you another example. So let's imagine that you have two RCs in parallel. Let's call this R1C1, R2C2. And let's say they're driven by an ideal voltage source, so they don't talk to each other. And what I do, let's say through an ideal buffer or whatever, so this has an infinite input impedance and 0 output impedance, I add them. And I define this as my V out. So what happens now? How many poles do I have? Each one of these two paths represent a single pole system. No 0, right? It's a low pass system. So this one has a time constant R1 C1, which is tau 1, and R2 C2 tau. But let's apply the method and see what we get. 0 is that, tau 2 0 is R2 C2. And in this case, since they're uncoupled, I can just write this as tau 1 and tau 2. But what's the overall transfer function? Of course, and then there's tau 2 1, which basically we argued is equal to tau 2. Equal to tau 2 0, which is tau 2. And the denominator of this thing, again, is almost exactly the same as last time. So it's going to be 1 plus tau 1, tau 2, s plus tau 1, tau 2, s squared. Which can be factored, of course, as 1 plus tau 1, s, 1 plus tau 2, s. Right? But now, let's see what happens in this case, in general, in the numerator. So let's calculate the h's, the transfer constants. What is h0? 1. Kind of, it's like 2, really. Just get 1 from here and 1 from there. And since you're adding, it's 2. Okay, doesn't matter. h1, what is h1? h1 is a transfer function when c1 is shorter, which is this path is killed essentially, this path is there, 1. And h2 similarly is 1. What is h1 2? 0. So what am I getting? I'm getting h1 tau 1 0, h2 tau 2 0. So I have 2 plus h1 tau 1 0 tau 1 plus h2 tau 2 times s, which is 2 plus, these are 1, this is tau 1 plus tau 2 s, correct? Which I can factor the 2 out and then get this tau 1 over tau 2, tau 1 plus tau 2 over 2, the average of tau 1 and tau 2. So we can write that tau 1 plus tau 2 over 2 times s, which is equal to neither one of those two. So they are not canceled in this case. So what happened? I started with 2 first-order systems with 2 poles, individually each one with 1 real pole, and I got a system with 2 real poles which are the same as those 2 poles, tau 1 and tau 2, which were the time constants of them. But then I got a 0. The left half my bona fide 0, which is at neither of these frequencies. In fact, the time constant is half in this case. And those are uncoupled. 2 poles are uncoupled. But through the parallel paths, I've created a 0. This is actually one mechanism you can create 0. Anytime you have 2 parallel signal paths or multiple signal paths, you create zeros. And that's actually one of the telltales of zero when you create 0. I'm just like, you can look at it and say, well, do I have parallel paths, signal paths? And I'll show you another example, a circuit example in a second. When you create a 0. And you see, although the poles are decoupled, the 0 is created. And this shouldn't surprise you. Remember, we said the poles are the natural frequencies of the circuit. The poles are independent of the definition of the input and output. But the zeros are not. The zeros can be affected by the way the input and output are combined. And you can see, you created one out of thin air. There's nothing bad happening here. But let's go back to your question earlier, right? You said this doesn't apply to zeros in general. They can be decoupled, but they may not be necessarily. So see, the fact that the poles are uncoupled doesn't mean anything about the zeros. In fact, we didn't have zeros, but now we do have zeros. The zeros are different. But sometimes if you have circuits that are completely uncoupled from each other, so you have like some circuitry here, and there's some buffer here, and then they're cascaded like that, whatever poles and zeros you have here are uncoupled from these poles and zeros. But if they're parallel systems like that, that's not necessarily true. So in general, this is not true. And this is a useful thing, actually. There's more detailed discussion about these parallel paths creating zeros and poles in the handout, I think number 12, the last handout from last quarter. So you may want to look at that and read that part. And there are different mechanisms 0. You can fit any system with 2 real poles and a 0 to this system by adjusting the right R's and C's and tau 1. And the good thing about it is that it allows you to calculate the time constant, because it says the sum of the time constant, the overall response, the time domain response, is the sum of these two time domain responses. So if the step response of this one is like this, and the step response of that one is like this, then you may get something like that. Just the sum of the two. And that allows you to determine where the relative position of the 0 with the poles should be to get undershoot, overshoot, etc. So does that answer your question? Really good. Okay. So you see, it has to be all consistent. It can't just like have. So yeah, it's true except for this case. You know, it has to be mathematically correct. You can't say, oh, a plus b squared is equal to a squared plus b squared plus 2ab, except when a and b are like 3 and 4. It can't be like that. Not useful. Okay, so now let's talk about infinite value time constants. Let's go and do it here. So you remember when on the first lecture we had on high frequency behavior, we said a transfer function in general, right, could be factored into 2 parts. A high frequency part and a low frequency part. A part that was a low pass response and a high pass response, right? We said, and we wrote it as a mid-band gain. So we said in general, if you have a band pass system like this with a mid-band gain, we said we could separate these and those into 2 parts and write them separately. And we spent most of our time dealing with these. And we saw that we can use our zero value time constant to estimate this omega h, which is the 3 dB frequency at which it starts dropping down, the high frequency cutoff. But there's an equivalent one that says omega L, low frequency cutoff. And that low frequency cutoff is also important because if you have, for instance, things that are AC coupled or things of that sort, then you need to determine that. And the question is, how do we determine that? So, in general, so now instead of focusing on this, so far we've been thinking about the following, right? So so far, we assume that if you had something like that, we've broken it into 2 parts, and we looked at the red part of the response. Now, you want to look at that was why we were talking about the zero value time constant frequency estimation. We said it's a low pass system. Just looked at that equivalent circuit. Now, there's another equivalent circuit, which is the high pass equivalent circuit, the blue one. And you can do a similar treatment of that, and that allows you to estimate this frequency. So let's see what it looks like. So let's think about this blue system, this high pass system. So how does the transfer function of this high pass system look like? Do you agree or disagree that it should have the same number of poles and zeros to get a high pass response? Because at infinity you want to have no drop, neither a drop or an increase, right? You have to have a flat response at infinity. So you have to have the same number of poles and zeros before infinity. So let's say it's an nth order system. So let's write it as 1 plus b1 s plus b2 s squared all the way to bn. Oh, here I have to be a little more careful. bn minus 1 sn minus 1 plus bn sn. Actually, this is lowercase n. And then in the numerator, I will have some 8n s to the n. This will give me a high pass response. I mean, it doesn't have to be like this. You can have all the other terms, all the lower order terms, a n minus 1, a n minus 2, but this is the simplest one that does that. And around that frequency, this is the one that matters the most anyway. So I have something like this, and this is a high pass response. This will give me a behavior like that blue curve. So I divide the numerator and denominator by this term. By this term. Like bn s to the n. So what do I get? I get a 1 from this guy. I get a bn minus 1 over bn over s Because if s goes to infinity, all of these terms become 0. That's what's left. So I'm really converting it to an inverse pole representation. Talk about it. So s, I have 1 over s. It's just the same it's a conversion. But it allows me to write this in terms of ambient band. The gain at that middle of the band. Okay, so this is what it looks like. So the question, would it be fair to say that around this frequency, this is really dominated, this drop? Because you start from high frequency and you come down, which term is the one that will affect you the first? This term, right? So around that frequency, we say around omega L, this can be approximated as a first order system like this. The same way that you remember when we had 1 plus Bn plus B1s, B2s, we said around this frequency is equivalent to this system. Okay? So now, this basically allows me to estimate omega F as what? As Bn minus 1 over Bn. The same way that we did estimate the omega H as 1 over B1. Remember that? It's just that's the mirror image of that, really. Okay, so that's omega L estimation. So the question is, what is Bn minus 1 over Bn? To tell you what that is, I'm going to show you a special example first for you guys to get a feel for it. And it's the second order system, and then we'll do the outputs. So for a second order system, how does this look like? So for a second order system, let's say you have A2s squared over 1 plus B1s plus B2s squared. So if I do divide this down by B2 and s squared, so this becomes my A mid, which is basically A2 over B2, 1 over 1 plus B1 over B2s plus 1 over B2s squared. Correct? And so in this case, basically I'm saying that my omega L is approximately B1 over B2. But what is B1 over B2? What is B1? In this, you know what B1 is, right? Tau 1, 0 plus tau 2, 0, right? The sum of the zero value time constants. And what is B2? It's tau 1, 0, tau 2, 1. Fair? So I can write it as the sum of the two. So I can write it as tau 1, 0 over tau 1, 0, tau 2, 1 plus tau 2, 0 over tau 1, 0, tau 2, 1. What is this? These guys cancel each other, right? How about these guys? Can I rewrite this in a different way that's more useful? You remember that identity that we have? What can I write it as?
The denominator.
Denominator as tau 2, 0, tau 1, 2, right? They're the same. And if I write it that way, this guy cancels that. So what am I left with? I'm left with tau 2, 1, 1 over tau 2, 1, plus 1 over tau 1, 2. In this case, these are the time constants of elements 1 and 2 when all the other elements, in this case there's only one other element, are infinite valued. So I show them as 1 over tau 1 infinity plus 1 over tau 2 infinity. This is tau 1 infinity, this is tau 2. This is a special example to see where it comes from. But then I'm going to show you in a minute that in general, this is exactly equal to the sum of the reciprocals of tau I infinities. I equals 1 to n. I haven't proven this yet, but I showed you a special case in the second order system that's true. And I'll show you it's like one line. But that's the result we'll try to arrive at. And this is the proof in the second order system. Any questions on this? Good. Alright, so this was the second order system thing. I'm going to erase it and do it for the nth order system. Just like a little bit of indexmanship. Ready? May you erase? No. general, I'm interested in Bn minus 1 over Bn. What is Bn minus 1? Bn minus 1 is a scary looking sum which is not as bad as it looks. Of tau I0, tau ji, tau kij, all the way. And what is Bn? Bn is actually a nicer animal, at least in terms of indices and sums. It only has one term, right? Bn is tau I0, tau ji, tau kij, whatever, like tau L, I, J, K, etc., all the way up to the nth term. This is up to the n minus. So here there are n minus 1 time constants, right? There are n minus 1 of these.
And there are 2 sets of this.
Say again?
And there are 2 sets of them.
There are n sets of these in general, because you can go through rotational combinations, right? For a second order system, there will be 2 sets of them. But for nth order system, there will be n of them, because you can basically just take them. Make I, J, J, K, J, make I, J, J, K, K, L, etc. Shift 1 and go through the rotation. So this is one term of n, right? And this is a term of n minus 1. So there are n terms, and the whole number of these terms. How many of these terms? So it's a sum of n terms. Each term is a product of n minus 1 time constants. So in each one of them, I can reorder these indices to match the n minus 1 that I have here. What is left is the last one. Right? It would be tau, I don't know, m, I, j, k, etc., etc., etc. So there are n minus 1 terms in, I'm sorry, n terms here, not n minus 1 terms. N. So it's the sum of n terms, and each one of them is n minus 1. So there are n of these, and each one of them is a product of n minus 1 terms. Time constant. Okay, so each one of them reduces to 1 over 1 time constant. So there are sum of n of these. So what is the first one? The first one is the sum of everything except for the first. So it's basically 1 over tau 1 when you have 2, 3, all the way to n. Sure. The second one is 1 over tau 2, 1, 3, etc. to n. The one in the middle somewhere is tau n, 1, 2, 3, n minus 1, n plus 1, all the way up to whatever, n. And all the way to n. So what are these time constants? This is a time constant for element n when all the remaining elements are infinite value. Same here. All the remaining elements. All the remaining elements. This cannot appear in the numerator, right? In the superscript. So I show these as tau infinity. So this is tau 1 infinity plus tau 2 infinity all the way to tau n infinity. So it becomes basically the sum of 1 over tau I infinity. I equals 1 to n. So it's a time constant associated with element I when all the other elements are infinite value this time. It's kind of the opposite of the 0 value time constant. Okay? Yes?
What happens if you consider the other terms in the numerator?
The numerator or the denominator?
Numerator, I mean a n minus 1.
Basically, they won't have an impact around here. See, around here, it's dominated really by, because you see these, then if you had lower order terms, you will have some sort of a, I don't know, a n minus 1 over bn s. Right? So this will have more effect than that.
But you're talking about the low frequency, so this term.
Right. That would mean, okay, but that for this to have the same effect as this one, it means that you have to have a 0 around here. And again, the same assumption that you had in the 0 value time constant. You assume that you don't have a 0 very near to this thing. Otherwise, it's fixed. That's why this is an approximation. But that's a correct observation. But that's why this is an approximation. And there are certain conditions that need to hold. If, for example, I can make an absurd example, right? I can say I have a 0 right on top of this pole. Then that pole is not really significant. Okay. So let's do an example of this. So this is the 0, the infinite value time constant. And how do we use it? How do we apply it? Let's go somewhere else. Okay, well, let's think about our common emitter again. But let's say this time I have one that's AC coupled. And only think about C pi. Well, C1. So, let's think about it. So this is basically a bandpass response, right? Because at very low frequencies nothing goes through, at very high frequency nothing goes through. So I can separate it into two equivalent low frequency equivalent and high frequency equivalent circuits, right? The things that stop things at high frequency I should put in the high frequency equivalent circuit, and the things that are affecting the low frequency circuit I put in the low frequency one. So my low frequency circuit looks like this guy at low frequency doesn't do anything, essentially, right? This is the transistor capacitor, limiting it at high frequency, low frequency, my equivalent circuit looks like this. And at high frequency, this guy is supposed to be a short. So I have an equivalent circuit that's like this. So if I want to analyze it this way, then it's easy, right? So it's the same kind of two first order systems I can analyze. So it's kind of like trivial at this point. What is that? What do I have? Do I have a 0 here? That was the only capacitor? No. I have a single pole. What's the pole time constant? Exactly. So this basically gives me something 1 over 1 plus tau pi S, where tau pi is R1 parallel R1 times 2 pi. And times the gain, basically, let's say H0. And here, I have what? Now, what do I have here? I have a pole. Do I have a 0? Yes, I have a 0, because if I short circuit this, then something goes through. Otherwise, I don't, nothing does. So in this case, H0 is 0. H1 is whatever that, well, let's call this H, or let's say ADC, or A mid, the mid-band gain, which is in this case basically R pi over R1 plus R pi times GM R2, the mid-band gain. So H1 is A mid. So I have a pole and I have a 0. The 0, the time constant is the resistance C minus guy, C1. What is it? R1 plus R1. This is different, right? And then the 0 is happening in what? So what is H1 is C1, and the time constant is this. So I get basically A mid times R1, or let's call this tau pi prime, or tau 1s, and this becomes A mid times tau 1s. See, I have a pole and a 0. So at high frequencies, this term doesn't matter, these two cancel, I get A mid. This gives me the high pass part of the response. this gives me the low pass particle response. Of course, I've simplified it to the minimum required, right? So in this case, I didn't need to really do anything fancy because I only had one capacitor. If I had more capacitors in this equivalent circuit, then I have to calculate their time constants independently to calculate this cutoff frequency. But then I have to, instead of adding the time constant, remember this is different. If in the zero value time constant method, right? We calculated time constants, added them up, and then calculated the 1 over that, right? So the estimate for omega h was 1 over the sum of the zero value time constants, right? In the infinite value time constants, you have to calculate the time constants, calculate the reciprocals, and then use that sum as an estimate. So in this case, omega L estimate, the estimate for omega, this is also an estimate, is going to be sum of the reciprocals of the infinite value time constants. You see they're different. And that's why this is dominated by the largest time constant, while these guys are dominated by the smallest time constants. Okay. So let me do something. Let's do something. Let's do a numerical. You remember we designed something? Yes. I'm listening.
In this example, in these circuits that you split it into two parts, low frequency and high frequency. For example, when you are analyzing the low frequency circuit, you are neglecting the effect of high frequency
Correct.
elements, and then for high frequency, you are neglecting the other one. So
Correct.
You are calculating two transfer functions which approximately show the behavior, the frequency behavior of that circuit, right?
Right.
For two different regions. But when you multiply these two transfer functions, the result, the final transfer function, which is the product of these two, is the exact transfer function of the circuit, or is it an approximation?
Not exact, no, it's an approximation. Actually, let me show you that first. It's an approximation, but it's a good approximation as long as you have a well-defined mid-band range. If you have a range over which the gain is pretty much constant, then this separation is valid and a good approximation. If you don't have something like this, if your transfer function looks like this, or worse than that actually, something like that, then you can't do this decomposition. I mean, you can, but the approximations are not very good. You can always decompose. You remember mathematically we could separate. The first thing that we did, we separated from the low band and high band, but then these would not be good approximations of those.
Well, if you
Let me just show you something mathematically. Let's do this without knowing what is high pass and what is low pass. We can treat it as a second order system, right? Let's do that. Let's do that with a different color. So, I can generally do this, right? I mean, it doesn't matter. I don't have to do it as high pass and low pass. I can always do it in general. So, what are the time constants of this thing? What is tau 1, 0? It's the same as that, right? But just managed to erase it. Tau 1 is R1 plus R pi C1. So C1 times R1 plus R pi. And tau pi 0 is C pi times R1 parallel R pi. Okay?
just
Oh yeah, you're right. Actually, I'm sorry. You're right. In this case, it's just R pi. Thank you. And then I have to calculate one more thing. This looks simpler, so I calculate the tau 1 pi. 1 with pi is short, it's R1. So it's C1 R1. Okay? So I know my denominator. My denominator is 1 plus R pi C pi plus R1 plus R pi C1 S plus the product of these two, R1 R pi C1 C pi. Okay? And then in the numerator I have something I can calculate. I think it's the same zero. So the only one that's non-zero is H1, right? H1 is whatever that then I have H1 times tau 1, 0. So it's A min times R1 plus R pi. This part doesn't matter really. But let's keep it. So that's the transfer function with S. Correct? Okay. I claim that I could factor it, right? Can I factor it? Exactly. Can they be factored? In general, for any values of C1 and C pi. For any values of C1 and C pi, the denominator cannot be factored. But let's just assume, make a reasonable assumption, because if you want this to work, C1 has to be much larger than C pi. This is a coupling capacitor, this is a parasitic of the transistor. If you make that assumption now, though, then what happens is what?
R1 plus R pi as R1.
Correct.
So you take that. And your B1
Actually-
R pi C1 plus R1 C1.
Right. So you can basically approximate this, or the other thing that you need to have basically is that R1 is much greater than R pi. No, not necessarily. So in that sense, actually we can write it then as R pi C pi plus R1 C1 S plus R1 R pi C1 C pi S squared. And then this can be factored. So a certain condition needs to hold. Actually, let's see what that condition is. I think the condition is that R1 needs to be greater than R pi. Let's see. Yeah, it seems that you need to have that condition, it appears to me. And if that holds, then this should be valid. But it should be valid also for C1. Let me look at this.
But you want to find those two time constants that you calculated, right?
Oh, no, actually that's correct. That was correct. Let's do this. Let's divide the numerator and denominator, because this part is also important, right? Let's divide the numerator and denominator by this term before we factor it out. So what we are left with is going to be 1 over R1 plus R pi C1s plus 1 plus R pi C pi over R1 plus R pi C1 times 1, nothing, just wait, that's it. And then you get this divided by that. Okay. You see? Now, this part is simply the high frequency time constant. You can write this as tau pi. So it becomes A min over tau pi S plus this term plus, what is this? This is the tau 1. 1 over tau 1 S. Okay? To be able to see, there are two separate parts. To be able to completely separate them, then if you assume that C pi is much smaller than C1, then this becomes 1. And then it works out. So you can see, but this is more difficult than doing this. So that's why you try to divide and conquer. Break it up to the smallest piece, smaller pieces as you can, and then you can go forward. Okay. Let me show you let's do a numerical example. So you remember we designed this circuit, we just basically say we had a cascode, we had a buffer at the input, and we can put a buffer at the output and all those things. So I have some of the values from those circuits that we did design. And let's make this into an actual circuit. So let's say you have to save time. So let's say you want to make it discrete design. You have a cascode state. then let's say you have plus minus 12 volts supply. And then I think you have something like 12 kilo ohms here. And then you want to have a buffer, a common collector here. And then I think you have like 2 kilo ohms of source resistance. At the input, and I had like a 5 picofarad of load capacitance. So this is something we've designed before, right? But now I'm going to bias it as a discrete circuit and get V in, V out, and everything worked out properly. So let's say my supply lines are plus 12 volts and minus 12 volts, and I want to get this bias properly so everything works out. So let's say I want to drive everything at 1 milliamp. Okay? I want this guy to be at 1 milliamp, so I need to set this voltage properly. Right? So to set this voltage properly, and I know that I need some degeneration here, some RE. So I pick 1 kilo ohm, so that drops 1 volt at 1 milliamp. So that gives me enough comparable to the, so it's comparable to the VBE of the transistor. So I can do AC couple or DC couple. Let's do part of a DC couple, part of an AC couple. See where it goes. So 1 kilo ohm, 1 milliamp, what is this voltage? So now I will measure all the voltages with respect, so all the purple values are with respect to the lowest voltage in the circuit. So how much above that I am. So this is going to be plus 1. Above that. When I say plus 1, I mean above the minimum. So what is this going to be? Plus 1.7. Now, if I want to bias, make sure that these are consistent, this has to be at plus 1.7. So I make this resistor maybe 1.7 kilo ohm. And then I have to bias this, and then if this is 1.7, what is this going to be? Plus what? Plus 2.4. So it means that this has to be plus 2.4 above the ground. So I have to get 2.4 volts out of the 24 volts. So I have like a 1 to 10 division, right? So I have like a, if I had a 90 kilo ohm resistor, I could put it here, and 10 kilo ohm here. That would give me a factor of 1/10 out of 24 volts, give me 2.4 volts. If I didn't have 90, I could put 85 and it would be close enough. And then, but this voltage, remember, what is this voltage at? Absolute. It's like minus 9.6. So I can't connect it directly here. So I have to put some sort of a capacitor. A lot of times you may have, I mean, if I want to make it exactly more interesting, I can put a capacitor between here, bias to 10. I'm not. Okay, I'm not done with biasing though. I have to bias this guy some meaningful voltage. What voltage would you make this bias at? Would you put it as high as possible or as low as possible? If I, as low as possible. Possible meaning before this guy goes to saturation. So to have a safe margin, if I put this at the same voltage as that, I have about half a volt of margin for this guy saturated. So I don't have much gain from here to there. So there's no risk of this swinging a lot and going to saturation. The gain from here to there is 1. The gain is happening really here, from here to there, the common bits, which I have to bias from still. But, so if I put this at 1.7, that's fine, and then that puts this base voltage at 2.4 volts too. So I have to have another 2.4, so I would use the same kind of resistors. By the way, this is something that works, I mean, if you just put it together on a breadboard or something. So now, the other thing is that, then what is this voltage at 1 milliamp? It's plus 12, right? It's 0. Right? Because it's 12 volts below plus 12 volts. It's at 0, which is a good place because you want to go both ways. This is where you have your swing. So that's fine. And then I drop 0.7 volts here. So this is going to be plus 11.3 volts. And if I want to bias it at 1 milliamp or something, then I can do it. Typically I would probably bias it higher than that 1 milliamp because this is driving the output, but doesn't matter. Just like for now, we can make this 11.3 kilo ohms.
Biasing it at 11.3.
Then that would give me 1 milliamp, right?
But your VCC is 12 volts, so
Okay.
will the base of the last transformer be 12 volts? It's by
No, 12, no, 12 plus 12. It's plus, so it's 0.
yeah.
So this is 0. This is plus 12, meaning plus 12, 12 plus minus 12 is 0, which is the middle, exactly the middle. This is exactly the middle. So this would be at plus 11.3, which means that it's basically at minus 0.7 absolute. When I say plus, I mean plus this. This is my reference. So this is like an absolute is 0.7, minus 0.7. So you can do it either way. Practically, you should make this like 5 kilo ohms or something. Drive this, like put this in 2 milliamps or something like that. Or a few milliamps. You could do that. Just do it right. So 11.3, let's say I want it at 5 milliamps and make this 2 kilo ohms. 2.2 kilo ohms. And then, okay. And then I need to do something about here too. Because the base, I assume that it's a low frequency, it's a short, right? When I make comments. But this is not short, it's a high impedance. So I have to put a capacitor here. So I have to decouple this one. And now, if I do it this way, I get very little gain, right? Because I haven't bypassed this guy. This was for biasing, remember? So I just want to bypass it so I get the maximum gain. So this is the bypass. And these are our big fat capacitors, right? So let's make all of them 1 microfarad. See what happens. And this was, I think, 5 nanofarad. So this is, I don't know what it is. So let's make it 5 nanofarad. They say if you don't know where you're going, you will end up somewhere else. So we'll end up somewhere. Anyway. Okay, so we know how to so what were our capacitors? We have a bunch of high frequency capacitors and low frequency capacitors. The high frequency capacitors are these guys. And we've done this before, right? We've done the zero value time constant. I wish we had time we could do both, but we're short of time. So I won't do the high frequency part, the zero value time constants, but you can do it. I suggest that you do it as an exercise for yourself and estimate the bandwidth of this and put it in splice and see what you get. This would be a good exercise. But now, how about the low frequency cutoff? At what frequency? At DC, obviously, this doesn't have much gain, right? I claim the gain at DC is 0. Do you agree? Because nothing goes through this guy. So, what is the gain? What is the estimate of the bandwidth? So, I have to calculate the zero value, the infinite value time constant. How many do I have based on the circle? 3, right? This guy, that guy, and that guy. So, let's calculate their time constants. So if I calculate the time constants, let's call this, I don't know, C1, C2, C3. What is the resistance seen by this guy? When all the other capacitors are, not the red ones, the blue ones, all the blue ones, because that's the circuit we're analyzing. All the blue ones are shorter. So if this is shorter, what you see here is R pi. You see 2.5 kilo ohms, and then compare the 1.7. So let's say 1-ish, 1 kilo ohm times 100, about 100 kilo ohms here, parallel with like 8, right? So it's 8 on this side and 2 kilo ohms on that side, it's 10 kilo ohms ballpark. 10 kilo ohms, 1 microfarad is 10 kilo ohms times 1 microfarad is gives me milli, so it's 10 milliseconds. Right? What is tau 2? What is the resistance seen on this node? It's like 8 kilo ohms to ground here, and then whatever you see looking to here, which is very large because you see the RO of this guy multiplied by beta, so it's pretty much the 8 kilo ohms. So it's 8 kilo ohms times 1 microfarad, that's 8 milliseconds. And tau 3 is emitter of this guy, and then you have to go to the base of this guy, but yeah, remember, this is shorted now. This is infinite value, right? So you see 2 kilo ohms here, divided by beta, gives you about 20 ohms. So you see 20 ohms here. That 20 ohms, in parallel with whatever it is, it's 20 ohms, divided by another beta, which is what? 0.2 ohms. 0.2 ohms. It's 200 nanoseconds. So which time constant do you think dominates? Remember now, this is the opposite. Tau 3. I mean, it's easy to see. You are summing the reciprocals of these. You're adding this 1 over these. The ones that gives you the smallest time constant gives you the largest 1 over. Right? So in the sum, this will dominate. This will have no effect. That's why this guy is typically much larger than that guy. These capacitors, bypass capacitors, have to be much larger than the decoupling capacitor because they see much smaller resistance. So what happens is that this is way too small. If I were to estimate the omega L based on this, I basically can ignore these other ones pretty much. Right? It's 1 over 200 nanoseconds. 1 over 1 millisecond is 1 megacycles per second. This is like 5 megacycles per second. So it's a little bit less than, if it were 6, it would become 1 megahertz, right? So it's like 800 kilohertz. That's terrible. If you're making an audio amplifier whose omega L is 800 kilohertz, nothing is amplified. Right? You want it, if it were an audio amplifier, what you would like your omega L to be? Ballpark. 10, 20 hertz, right? Tens of hertz, not hundreds of kilohertz. This is not going to work, actually. It's going to have very little gain. You've designed it for much larger gain, but you get the gain of basically this capacitor not being there, just make 12 to 1. Yes?
Well, now that we calculated tau 3 and we saw that it's a very small time constant, can we conclude that it has, it can be considered a high frequency part circuit too?
No. Because what it does, this creates a pole and a zero. This is an inverse pole. What can happen is that, it depends on what these capacitors are. I mean, if you're cut off, so for instance, if your omega H is 1 megahertz, then it means that the omega L and omega H are overlapping, so basically you don't have a flat gain region, which means that it's a bad design anyway. But the more important conclusion that you can arrive at is that we picked this value too low. You have to go to a much larger value, say 1,000 microfarad, 1 millifarad. If you go to that, then this becomes nanoseconds become milliseconds. I'm sorry, microseconds. Use a different color. 200 microseconds, and this basically becomes 80 hertz. Still, 800 hertz. Still not good. That's not good. So that's be larger. 10 millifarad. Actually, it's not that bad. I'll tell you why it's not. It doesn't need to be this large in a second. Practice. That 1 millifarad was good enough, but I made an approximation here. So this makes this like 2 milliseconds. Now, if it's 2 milliseconds, then I have to really add all of them up, right? Because then these are countable. So that gives me 1 over 5 milliseconds. So basically 1 half plus 1/8 plus 1/10 of 10 to the 3. So it's 0.5 plus 0.1, 0.6, it's 0.7-ish. So it's like 700 cycles per second, which basically is approximately around 120 hertz. That's acceptable. Probably the sound that comes out of it is not going to be that terrible. Of course, if you want to make it perfect, when you go down to 20 hertz or something like that. But that's an estimate, right? That's the estimate. And then you can see it's pretty close. analysis simulation. The reason is that I actually ignored one thing that was very important in this thing. The RB of the transistor, the base resistances. In this case, they matter. Because if you assume like even 100 ohm, or more practically like 1 kilo ohm of resistance here. Yes, this is 2 kilo ohms, this is 3 kilo ohms, fine. Divided by beta gives me 30 ohms. But that 30 ohms is in series with 1 kilo ohm again. So this resistance cannot drop below a certain minimum. So 30 ohms are in series with 1 kilo ohms, like still 1 kilo ohm, divided by beta, it's going to be 10 ohms. So it can't really go below 10 ohms, because it's the RB of the transistor itself. So if it were 10 ohms as opposed to 0.2 ohms, then this would be like 50 times larger. So this really didn't need to be this big in practice, if you had I taken that into account. But anyway, so that you get the idea.